Now, uh, let people join me now. All right. So we're starting off. So let everybody join so that we can have this lecture right now. Digital logic gates. Digital logic gates. In electronics, we have a analog electronics. Right now, we want to learn about digital electronics. All right? We want to learn about digital electronics. And digital electronics, the basics of digital electronics is the digital logic gates. And we are learning it, their theory, their schematic, diagram, and the rest. That's what we are learning today. So please pay attention. So like I said, we are learning about digital electronics. And the basic things we are learning, they are the logic, the basics of logic circuits, logic gates. Logic gates. We have what we call gates in digital electronics. They are not gates to a house or to a particular door, a particular compound. Rather, they are called gates because of their behavior in circuits. We have various type of gates. Various type of gates. We have the OR gates. OR. Now, the OR is a logic function. Also, we have the AND gate, AND. We have the NOR gate, NOR. Then we have the NAND gate, NAND. We also have the NOT gate, NOT. Also, we have XOR gate, XOR. Likewise, we have XNOR. These are the basic gates that we have. These are the basic gates that we have. So we want to look at the theory of these gates. So each one of them has a schematic symbol that we use in circuits. And we're going to learn about that. We're going to learn also some of them that we can represent using switches in circuits. We're going to look at how we can do that. Lastly, we're going to learn about the truth table for each of the gates. Truth table for each of the gates. I'm learning about that. I'm going to have the truth table. I'm going to learn the schematic symbol. I'm going to learn the circuit representation of some of them also. So these are the basic things we are learning in the digital electronic class for today. All right. So if you haven't subscribed to the channel, don't forget to please subscribe. Click the subscribe button. Also, smash the notification bell so that you can be notified another time when we bring lectures like this or some other videos when they are uploaded. Please make comments. I will also personally respond to your questions. If you have any questions, I will answer them personally. So don't forget to do that. We appreciate that. Thank you very much. Now let's look at the OR gate. The first one is the OR gate. OR gate. The OR gate. The OR, the term OR, is taken from English, but is a logical function. A logical function. First, let's look at the OR gate, the symbol. The symbol looks like this. And when you look at it, we have the symbol here. What we have here now is a digital logic circuit that has inputs and outputs. Here we and then it always have one output, one output. Okay, all right. So dry one. Okay. Now the gate may, depending on the type you are using, we can have the one that has three inputs, not always two inputs like this one. But this is just the simplest form of it that we can use to explain. We need the simplest form of it. Okay. All right. Now, okay, this is wet. We need dry one. All right. So the simplest form of it is these two circuit logic gates. Now, marker is having problem. All right. This is the OR gate. I want to represent it with a circuit. We have switch here, S1. We have another switch, S2. The circuit goes this way, and we have this is switch S2. We have the source of power here, and we have a load. For instance, a lamp. We have a lamp here that we want to turn on in these circuits. All right. Okay, this is the lamp. We want to turn it on. Before this lamp can turn on, we need this circuit to be completed. How do we complete this circuit? We can complete this circuit by turning either switch S1 on or switch S2. Or better still, two of them can be turned on at the same time, and then power will connect to the lamp here, and the lamp will be turned on. All right. So it means either of S1 or S2, or the both of them can give us an output. That is the function, that is the behavior of this OR gate, two input OR gates. If there are three inputs, we can use another switch, parallel again. So the OR gate functions as two parallel switches. Two parallel switches. Okay. Now, let us now write out the truth table for this. Truth table. We have what we call truth table that gives us the function of a logic gate. If this is A, B, and the output is called Y, then we have A, B, output Y. A, B, then output Y. Because in digital circuit, we always have two states, 0 or 1. And that's why they call it binary system. 0 or 1, two states. Those two states can be taken to power of the input to the gate or to the circuit. So 0 or 1, 0 or 1, two states. So these two we raise it to the power, of the input. Here we have two inputs. So the number of combinations that are possible, the possible combinations that we have here will be 2 raised to the power of the inputs, number of inputs. That is 2 raised to the power n. N here is the number of the inputs. I'm very sorry for this marker. Okay, 2 raised to the power n. So in this case, we have 2 raised to the power 2, and that is 4. So we are going to have 4 possible combinations here. So we're now going to write them out in this manner. 0, 0, 1, 1. 0, 1, 0, 1. All right? So these are the possible combinations. Now, what will be the outputs for each one? Let's look at it. When there is no, high inputs, at the two inputs, then we are not going to have an output. That is, none of these switches is turned on. In that case, we are going to have 0 at the output. All right, is 0 at the output. Okay. When the first switch S1 is turned off and the second one is turned on, then we are going to have an output. All right. When switch S1, that is A, is turned on and S2 is turned off, 0, we are still going to have an output. Likewise, if both of them are turned on, we are going to have an output. Here, 1, 1, 1 indicates the output at Y is high. 0 indicates a low output. And then we can see the combination that gives us the output. The combination of the inputs. When we have 0, 0, we have a 0. 0, 1, we have a 1. 1, 0, we have a 1. 1, 1, we have a 1. And that's how the OR gate functions. The two input OR gates. Like I said earlier, we can have 3 inputs. If it is 3 inputs, it means we are going to have more of the rows here. If it is 3 inputs, then we are going to have 2 raised to power 3. And that is 8. We are going to have 8 rows. 8 rows. Okay. That is how the OR function works. Now, let us move on to the AND gates. Let's look at the AND gates. I'm going to check the AND gate right now. Don't forget to share and like the video. Okay. The AND gates can be represented by series switches. Series switches. So if you have an AND gate, you can imagine it to be a series switch. A series switch. Okay? All right. So the symbol, first of all, let's have the symbol of the AND gate. The symbol is like this. Inputs, inputs, outputs. So we can have inputs A and B, outputs Y. Now if I want to represent this one using switches in circuits, we can have something similar to what we had earlier. Switch, another switch, S1, S2, then power. Then we have a lamp that we want to turn on. We have a lamp here that we want to turn on. Now you will realize that before we can turn on this lamp, before this lamp can turn on, we will need switch S1 to be on and switch S2. So S1 and S2 must be on. Take note of the function and S1 and S2 for a 2 inputs AND gate, like this, for a 2 inputs AND gate. Now, if one of the switches, let's say S1 is turned on, while S2 is not turned on, what do we have? We are not going to get an output. We are not getting an output. Okay? Likewise, if S2 is turned on and S1 is not turned on, we are not going to have an output because current will not flow around the circuit to energize the lamp. So in that case, the lamp remains off. That is 0 state. So to represent this, we can use the truth table to represent that. We have truth table here. A, B, and Y. So we have 0, 0, 1, 1. 0, 1, 0, 1. Okay. So as we have this, for the function and this gate, let us look at the output that we are going to have. 0 and 0, we are going to have is 0. 0 and 1, this one is off, one is on. We are still going to have is 0. 1 and 0, we are going to have is 0. But 1 and 1, we have a 1. And this is the simple function of the logical AND gate. This is the way the logical AND gate functions. Now, this is only a 2-input, the most basic AND gate. You can have 3 input, 4 input as the case may be. But what you have to bear in mind is if it is 3 input or 4 input, until all of them have a high signal, we cannot have a high output. That is a logical AND function. Alright. Now let's look at NOR gates. NOR gates. Okay? First of all, we are going to get the symbol of the NOR gate. We're going to have the symbol. The NOR gate is looking like the OR gate, but has a bubble at the output. A bubble, that is the 0 at the output here. So this is 2 inputs, 2 inputs, NOR gates. NOR gates. All right? As it is, we want to look at the truth table for the NOR gates. If you have input A, B, output Y, let's look at the truth table. 0, 0, 1, 1. 0, 1, 0, 1. For the NOR gate, it inverts the function of the OR gate. A logical NOR gate inverts the function of the OR gate. That is, it gives us the direct opposite of the output expected with an OR gate. Direct opposite. So when the OR gate is supposed to give a low, the NOR gate will give a high. When the OR gate is supposed to give a high, the NOR gate will give a low. That is inversion of the functionality. So let's look at it. 0 and 0, we are going to have a 1 here. 0 and 1, 1. 1 and 0, 1. 1 and 1, 0. This is a logical NOR gate. We see that this is direct opposite to the OR gate that we discussed earlier. That is the logical NOR gate. It is an inversion, a direct inversion of the functionality of the OR gate. Right now, we want to go on to the NAND gate. Now let's look at the behavior of the NAND gate in circuits. So let's look at NAND gate. Okay? The NAND gate is also a direct opposite of the function of the logical AND gate. It gives us the direct opposite of what we get from the logical AND gate. So when AND gate is supposed to give a low, the NAND gate gives a high. When the AND gate is supposed to give a high, the NAND gate gives a low. So first of all, we look at the symbol. The symbol is the symbol of the AND gate with a bubble at the output. output here, Y, and this is input, A and B. Okay, so this is the symbol. So let's now look at how the truth table looks like. A, B, Y, 0, 0, 1, 1, 0, 1, 0, 1. Since it functions as an inversion of the NAND gate, we are supposed to have just the output of the AND gate inverted. If it's supposed to be 0, then we get a 1. If it's supposed to be a 1, we get a 0. So 0, 0, 1. 0, 1, 1. 1, 0, 1. 1, 1, 0. Okay. Okay. Yes, this is how it functions. This is how the NAND gate functions. When we have input here as 0, input here as 0, for an AND gate, we have a 0 here. But this is NAND, we are going to have a 1. Likewise for here and here. But when we have two of them, I, 1 and 1, entering into the NAND gate as inputs, then we are going to have a low output, inverted. So this is a logical NAND gate. NAND gate. NAND. The NAND is simply not and. Not and. Likewise, the NOR gate is not or. Not or. Now let's look at that NOT. That's a gate. That is that inversion gate, the NOT. And that's what we're looking at next. That is the NOT gate. We want to look at the NOT gate itself. The NOT gate now. The NOT gate is the simplest of all the gates, and it's usually having only one input and one output. And it is called an inversion gate. Inversion. Inversion gate. Why? This is because when you give a high to the gate as input, it gives you a low at the output. It changes the logical state to the opposite. Likewise, if you give a low, it inverts it and gives you a high at the output. And this is the symbol. You could see the bubble at the output. That is the NOT gate. This is the NOT gate. And the truth table is simple. If you have A here, what you're going to get here is A bar. That's the output. A either 0 or 1. Then we're going to have output as A bar, 1 or 0. The A and the bar on top of the A indicates inversion. That is, when A is 0, A bar will be 1. When A is 1, A bar will be 0. In some textbook, they use a different notation, something like this. A complement. That is inverted A. Inversion of logic A. So when A is taking 0, this will be 1. When A is taking 1, this will be 0. Okay, so that is the NOT gate. This is the way the NOT gate functions. All right, right now, let's move on to another one, which is another interesting gate among the logic gates. That is the XOR. XOR gates. XOR. XOR gates. I believe we are following. Let's look at the XOR gates. We have looked at OR gates, we have looked at NOR gates. Now, XOR. XOR is a very interesting gate. Basically, it's an OR gate that doesn't take multiple I inputs. Excuse me. The symbol looks like this. If you check this, you see that this is symbol of OR gates. But the difference now is that we have another hack at the input here for the XOR gates. Excuse me. So now, how does this gate behave? Now the XOR gates ensures that we have a high output when either of the inputs, when we have two inputs for instance, A and B, and here is Y. Either of the input is high, then we're going to get a high at the output. If A is high and B is low, we have output high. Or A is low and B is high, we have output high. But when both of them are high, A is high, B is high, we are going to have output low. And when both of them are low, A is low, B is low, we are going to have output as low. So for that, we have the truth table like this. AB 0011 0101. So for 0 and 0, we are going to have a 0 low output. 0 and 1, we have a 1. 1 and 0, we have a 1. 1 and 1, we have a 0. The ordinary OR gates, we have a high when both of them are high. But the XOR is not like that. All right. Okay. So this is XOR gate. Now, let's look at a similar gate, which is XNOR gates. XNOR gates also behave in an interesting way, similar to the XOR gates. So, we check the symbol. We also check the truth table for the gates. Now we are dealing with XNOR. XNOR. Another interesting gate. For XNOR, we are going to have a bubble at the output. So I changed the symbol for the XOR gate to get the XNOR. Now, how does XNOR behave? When you have the inputs here, ordinary NOR gate ensures that when you have a low and a low, you have a high at the output. When you have a low and a high, ordinary NOR gates will give you a low. You're not going to get a high. Now, the XNOR ensures that when the two of them are low, you are not going to have a high. That's the difference. So let's see the truth table. Zero, 0, 1, 1. 0, 1, 0, 1. Okay. For the ordinary NOR gates, what we have is this. When the both of them are 0 and 0, you have, a 1. 0 and 1, we have a 0. Okay? 1 and 0, we have a 0. Then 1 and 1, we are supposed to have, a 0. But right now, we are going to have a 1 because this is XNOR gate. That is XNOR gate. Okay? So it's an inversion that changes the functionality of the NOR gate. The ordinary NOR gate will give you 1, 1, 1, 0 here. Okay? Pardon me. When the two of them are okay, pardon me, for the XNOR, 0 and 0, for the ordinary NOR gate, we are going to have a 1, but when the two of them are this, it gives us a 0, rather than giving us a 1, because the two of them are low. Okay. And then when one is low and one is high, ordinary NOR gate supposed to give us, a low, and a low here. Okay, and this is supposed to be for ordinary NOR gate. Here supposed to be 1. Here supposed to be 1. And here it's not going to be 1 and 1. It's going to be a 0. And that is it. This is the XNOR gate. That is XNOR gate. Okay. It's an interesting gate. Now we want to look at some combination of logic gates and try to write out the outcome of combination circuits in logic gates. Let's give an example. We have a condition such that we have some functions. We have an OR gate here. Two inputs. Okay. A and B. We have this input B having a NOT gate, okay, and is going into an AND gate. All right, and the input A also goes into the AND gate. Also, we have a NOT gate, a NOR gate. The NOR gate is having the inputs A having a NOT gate introduced, and then input B is coming, and then the output of these three gates are now entering into one final gate, which is actually an AND gate. AND gate, not NAND, AND. And this is the final output. This is an interesting circuit, and we want to look at what will happen at the output. Okay. What will happen at the output? We have OR gate here. So if you look at the intermediate outputs, then we see what will happen. Let me mention that the wiring here indicates that when we have a dot, it indicates that there's a connected terminal here where the signal is tapped through another gate. But when they cross each other like this, there is no connection. For instance, this one, there is no connection, but here there's a connection, there's a connection here, there's a connection here, and there is a connection here. Okay. All right. Now I want to look at what will happen to the gates and what will be the final output. What will be the final output? Okay. Now, intermediate positions, that's what we want to look at first. At this point, we have a B bar, B bar. At this point, we have an A bar, A bar. Okay. And so, each gate will have its own output, the intermediate gates, the OR gates, the AND gates, and the NOR gates. So let's call the intermediate output here L, here M, and here N. So we're going to look at what we get, what we're going to get as at these 3 points. Let's look at the truth table. We use this small space L, M, and L before we get the final output, which is Y. There are only 2 inputs, A and B, 0, 0, 1, 1. 0, 1, 0, 1. Okay. All right. So let's look at intermediate output L. Intermediate output L, that's this point. We have an OR gate, and then the input to the OR gate is A and B. For A and B as an OR gate, we're going to have 0, 1, 1, 1. All right. Now, intermediate output M, we're going to have A as an input and B bar as an input. So, A and the inversion of this column will be handed, logic hand, to get the output A. Remember, for the AND function, all the input must be I before you get a I output. All right? So let's look at it. Inputs A and B bar. So let's look at it. A and B bar. A is 0. Once A is 0, even if B bar is 1, then the output of this AND gate will be 0. Let's have that in mind. Okay? Similarly here, A is 0, and then the inversion of B will be 0 also. So we are still going to get a 0 here. Next one. A is 1 when B is 0. So inversion of B will be 1. So 1 and 1 will give us a 1. Here, A is 1, B is 1. So inversion of B will be 0. 1 and 0 will give us a 0. That's what we have here. Okay, let's look at intermediate output N. For output N, what we have is this. A bar is going into the gates as an input, then B is going in as an input. So we're going to look at inversion of A with a logic function between that and B. So what do we do? Let's look at it. Inversion of A, this is NOR gate. NOR gate. Mark you, when you have inputs as 0 and 0, you're going to have 1. 1 and 1, you're going to have 0. 1 and 0, you're going to have 0. So that is how the NOR function behaves. So let's look at it. We're going to look at A bar, that is inversion of this column with this column. Inversion of A will be 1. 1 and 0 will give us a 0, a NOR gate. Version of this is 1. 1 and 1 supposed to give us, if it's ordinary OR gate, it will be 1 for here. Alright? So that gives us 0 also. Here, 0 and 0 will give us a 1. And also, inversion of 1 will be 0. 0 and 1. 0 or 1. That gives us a 0. So let's go over it again to be sure that there's no mistake. Inversion of 0 is 1. 1 nor 0. 1 nor 0. That's what we have. So it's going to give us a 0. 1 nor 1. 1 nor 1. Okay? 1 nor 1. What does it give? It gives us a 0. Here, the version of this will be 0 nor 0. Then we're going to have a 1 at the output. Here also, the version of 1 will be 0, 0 nor 1. 0 nor 1, we're going to have a 0 at the output. That is the behavior of the NOR gate. So this is output N. Now we have the intermediate outputs L, M, and N. They are now here. So the three of them will now serve as an input to the final AND gate that gives us the output Y. So we need to look at these three columns, L, M, N, entering the AND gate to get an output at Y. All right. So let's check that. The behavior of the AND gate is such that it is only when all the inputs are high that we can get a high at the output. When one of the inputs is low, definitely we are getting a low at the output. So let's look at this. 0, 0, 0 gives us a 0 at the output. It gives us a 0. Sorry for this marker. The mouth is spoiled, so that's why it's misbehaving. Okay. Now let's look at the second one. 1, 0, 0. Once we have at least one of the inputs as 0, we are going to get a 0 at the output. Okay. Next one, we have 1, 1, 1. The three of them are high. Surely we are going to have a high at the output. Next, we have 1, 0, 0. At least one of them is a low. For that reason, we are going to have a low at the output. So that is the result. So the output Y will be when we have the combination of inputs A and B as this, we are going to have an output as 0, 0, 1, 0. And that's very interesting. It's a very interesting output that we have there. So we see the combination circuit is simplified by this truth table by having intermediate outputs L, M, and N from the gates here. Of course, A bar and B bar, they are also intermediate gates, but we do not bother to put them on the truth table. But they were actually employed in getting the intermediates where necessary. All right. So this is the behavior of the combination logic gate that we have. What we need to know also in logic circuit is that when you have a combinational circuit, we need to simplify the final expression so that we can have the simplest circuit to implement. So the simplest circuit to implement will be the one that we have actually simplified the combinational circuit. Then we simplify a combinational logic circuit by means of Boolean algebra or by means of Kernoff map. Boolean algebra or Kernoff map. So that is how we simplify a combinational circuit. All right. So if you have any question, I would like you to please type your question. If it's clear, if you can see the screen well, let me know that you can see the screen clearly. All right. Okay. So let's look at the expression, the Boolean expression for this combinational circuit. Y. Y equals. I'm very sorry. The only marker I have around is bad. The only marker I have around is bad. Okay. Y equals. All right. early mn. That is to say, L dot M dot N. That is an AND function between L, M, and N, and AND function between them. That is what gives us Y. But what is Y? What is L, M, and N? We need to write it. So we are not going to leave it this way. Y equals L itself is A plus B. A plus B. I want to mention that the symbol for the OR gate is plus, but that plus is not arithmetic addition. It is a logic addition. That is the symbol for OR gate. So here is read A or B, not A plus B ordinarily. So we have A or B, then another bracket, because this is AND gate. The bracket here means AND function between L, M, and N. So in some textbooks you see a dot in between. If you don't put dot but the brackets are there, you are still okay. So we are not putting dot here. M, the function M is actually A dot B bar. A dot B bar. A B bar. And the final one, NOR gate, is actually A bar with B. A bar NOR B. A bar NOR B. Okay? A bar A bar or B, then we're going to have a final bar here. The final bar indicates that that is a NOR function that has been inverted. So this is what we have as the expression here, the Boolean expression for the combinational logic gates that we have on the board. Okay? So what we do now is we simplify using Boolean algebra. Now, the laws of Boolean algebra, we have the associative law, we have the commutative law, we have distributive law, we have inversion, and then we have De Morgan's theorem. Now, what we have here, it will be easier to simplify if we use a De Morgan's theorem. We can use De Morgan's theorem to simplify what we have here. Also, the simplest way to simplify is also the Karnaugh map. Karnaugh map. And both Boolean algebra and Karnaugh map will be taken in another lecture, not in this lecture for today. So, but I want us to realize that what we have in a when we have a combinational logic like this, we always write out the Boolean expression. This is the Boolean expression for this circuit. All right. Now, we can take another one, perhaps by changing the output here to an OR gate. When we change the output to an OR gate, then we're going to have a different output here. And that's what we're going to do. Then we are going to write out the final expression also. So let's try that as our last example for today. So we're going to change the final gate to an OR gate. And we're going to write out a new Boolean expression and get the final output on the gates on the truth table. We're going to rewrite that. Okay. So the final gate here right now is an OR gate. This is an OR gate. Okay. Now this OR gate will behave differently from the AND gate that we had earlier. All right. So we want to determine the output Y based on the three inputs getting into the final gate. The three inputs are L, M, and N. So the three of them are here. They form an input, a combinational input to the OR gate here. So let's look at it. For the OR gate, remember, when at least one of the inputs is high, then we are getting a high at the output. But when all the inputs are low, we are getting a low at the output. So if all the inputs are high, or 2, or 1, then we are going to get a high at the output. Let's see the results now. LMN, they are here, LMN. All of them are low, 0, 0, 0. Then we are going to have a low at the output. Here we have a high, a low, and a low. In that case, we have a high. Here, all of them are high. 1, 1, 1. Then we have a high. Here, 1 is high, and the remaining are low. So we are going to have a high. So this is the final expression on the truth table for the combinational circuit that we have here. Okay. Now, we can also write out the Boolean expression for that. Let's write out the Boolean expression for this. Here is an OR gate, not an AND gate any longer. So we can have Y equals L plus M plus N. L, M, N. They are now entering an OR gate. So if it's an OR gate, we're going to write out the expression for L, M, and N, and then put them out as OR function into the Y. And this is what we have. Y equals L is an OR gate between A and B. So we have A plus B. Then plus M. M is an AND function between A and B bar. So we have A, B bar. And N is a NOR function between A bar and B. So we have A bar plus B all bar. This is a NOR function. So this is an expression for the output of the combinational circuit. And it is this expression that we now go ahead and simplify using Boolean algebra or Karnaugh map. And that is a subject of another video in this series. So this digital electronic gate series. I'm going to learn that in another lecture. For today, I want you to ask your question so that we can respond. Don't forget to give a like to this video. And likewise, share the video. And if you haven't subscribed, kindly subscribe to the channel so that another time when we are bringing new video or lectures like this, you will be notified by YouTube. So thank you very much for joining. I want to see any question this live so that we can quickly answer that. All right. So we haven't seen any question. Does anybody have a question here so that we can quickly answer it before we leave this live class? Please ask your question. Ask your question. I'm very sorry for the poor marker I used. Some are not very, very bold, like the way I want it to be. So, if there are no questions, let's quickly do a summary or review of what we studied today. We're going to have a review. Bear in mind, we started with digital logic gates. We started with the representation of logic gates, their schematic symbols. We looked at the truth table of each. And we also look at a simple electrical circuit to represent some of these logic gates. All right? So we want to see the review. We want to review some of that. So let's see it. Let's see the review of this. So I want to rub this so that we can have a review of what we did. So we have the OR gate, OR function. OR function, that is the gate that looks like this. This is simply the basic one with 2 inputs and 1 output. Like I said, we can have multiple inputs, 3 inputs, 4 inputs, even 5 as the case may be. It can be more than that depending on what you are constructing. And I said the symbol for this function is a plus. So here we can write output y equals A or B. This is A plus B in mathematics, but in logic, it is not A plus B. It is A or B because it's a logic function. It's a logic function. We have the AND gate. AND gate. Symbol is this. AB. And this is output Y. Y equals A dot B, that is AB. That is for the AND gate. So the sign is the dot. For this function, the sign for this function is the dot, which is multiplication in mathematics, just like in mathematics. Then we have the NOT gate. Let me mention the NOT gate first. The NOT gate is the inversion gate, the gate that changes the logic condition to the opposite. So that is what we did. We also learned about the NOR function. The symbol A and B, and this is Y, and Y equals A plus B bar. That's an inversion because of this bubble. The bubble indicates that there's an inversion of the state of all gates to form the NOR gate. All right. Then we also looked at the NAND gate. The NAND gate. A and B. A and B. And then we have Y equals A dot B bar. So I'd like you to go ahead and practice combinational circuits, check questions offline and online to practice combinational circuits. These are the most basic logic gates that we looked at. We looked at XOR and we looked at XNOR. All right, those are the basic circuits, basic logic gates that we looked at today. Don't forget to like and share this video. Give us a thumb up. All right, smash the notification bell so that another time when we bring new videos like this, you'll be there also to be notified. So thank you very much for joining. Let me see if you have any question so that we can attend to that. All right. Okay, I see that everybody is following. Everybody is following. So I want to see question now. If there is no question, then we end the class. Okay? We end it. So I'm waiting for your question. Don't forget, these are the basic digital logic gates that we dealt with today. So the video will be available on the channel so that you guys can log on and watch again. Any part that is not clear, you can revisit the channel and watch it again. So until another time when we are going to have beautiful lecture like this, so I want to say have a nice day. Okay. Somebody asked a question. Okay. Yeah. You can digest it and then ask questions later. Come back to the channel, ask questions on the video. The video will be available shortly. YouTube will put the video available, make it available on the channel shortly so that you can ask your question on any parts of the video. Then I will attend to that. I will personally attend to your question on the channel. So right now, the live class is going to its end. Thank you for joining the class. Until another time. Don't forget, I said our next discussion that will be a subject of another video will be the minimization of combinational circuits. Minimization of combinational circuits. Combinational circuit minimization. Combinational logic circuits. Combinational logic. We call it combinational logic. Combinational logic. What does that mean is when you have several logic gates combined to give a special logic function in circuits, it is called combinational circuits. And combinational logic is very interesting. But like I said, when you have several logic functions wired together, you do not go ahead and buy all the gates and implement, but rather you simplify. You simplify the combinational logic first to the simplest form before you begin implementation. So that is why I mentioned Boolean algebra. So the combinational circuit will result into a Boolean expression that we can employ Boolean algebra to minimize. I also mentioned, out of the Boolean algebra, I mentioned there are so many laws under Boolean algebra, such as a distributive law, associative law, distributive law, associative law, commutative law, commutative law, and then there is involution law. Then there is De Morgan's theorem, De Morgan's theorem. All of these are employed to simplify a long Boolean expression that is obtained from combinational logic. Very long Boolean expression can be, scary when you have it. But when you know all these laws, Boolean algebra, you will be able to simplify such expression. I also made mention of Karnaugh map. So if you check the channel, you will see lecture on all of these. We have a lecture where we learned Karnaugh map it was a live lecture, I think. It was a live lecture. If you check on live, you will see the lecture on Karnaugh map. We have several examples how to simplify a combinational logic using Karnaugh map. Then there's another lecture whereby we treated Boolean algebra. So check under the videos, you must see the information on this. So that is that for today. We are going to stop here for now. Until another time when we come with live lecture, we say bye-bye. If you haven't done so, please subscribe the channel, give a like, and share to the video.